Hi, so today we will be going through complex numbers. So what are complex numbers? Complex numbers are numbers that combine real and imaginary numbers. So before we get into complex numbers, we need to probably go through what imaginary numbers are. So imaginary numbers are numbers such as this. I is equal to the square root of -1. So I is equal to the square root of -1 is an identity that is very useful because in real terms, there is no such thing as a square root of -1. However, if we expand it through imaginary numbers, we get a whole range of useful mathematics. So I follows a lot of the imaginary numbers follow the basic operations. So we can have I plus I would equal to 2i, for instance, right? And that'll be exact same as 2 roots -1. Great. And so next we have I minus I, which would simply be 0 I times I, which is the same as I squared, which is the same as square root of -1 squared, which would just be -1. And I divided by I would be 1. Now, the general form of a complex number usually follows this. So if it has a real and an imaginary part, it would be written in this format: a plus bi. So a plus bi, where a and b are elements of real numbers. So a and b are real numbers, right? So this again can follow a lot of the basic operations. However, you have to make sure that in these operations the like terms are together. So for instance, let's just have z plus z. This would be a written out, a plus bi plus a plus bi. Now we want to put like terms together, so we got a and we have bi. So all the real terms, which would be a, be together, so that's 2a, and the imaginary terms would be together, so that's 2bi. So that's the result that we would get. Z, again, if it was the same, it would just be 0, z minus z, and again, z divided by z would just be 1. I'll just write them quickly because there's not really much to show with these examples. But we also have z times z. Now, this would be a plus bi times by a plus bi. Now, how we would do this is similar to how you would use how you would do expanding the brackets for when you have unknowns, right? So when you have questions such as 1 plus 3x times by 2 plus 4x, right? It's the exact same way. So in this one, you would use the for method, which is first outer inner and last, right? So let's do that here. So the first one would be a times a and so that would be a squared. We did outer, a times b, so that would be plus a bi. Then we do the inner, which should be another abi, so plus abi, and a bi times by bi, which would be b squared I squared, right? Or you could have it in just a bracket as well of this would be the same as bi squared. But I'm going to do it this way just so you can see. So that would be, then simplify it further, I got a squared, and then these two are like terms, so we can add them together. So we got 2ab, they're like terms because of the I, it's the same. And we have b squared I squared. Now here, if you remember, we saw that I squared is equal to -1. So this would be b squared times by -1, which would give us minus b squared. So this would be the solution to z squared, z times z, right? Just make sure it's okay. So we also can have another identity known as the conjugate, right? So this is similar to irrational numbers. So the conjugate of our z here, which is a plus bi, would be, let me write it here, should be, the conjugate would be z star, and this would be a plus, sorry, that's the basic point. So a minus bi. This would be conjugate. And it gives us a lot of interesting identities when we do operations with them together. So for instance, if we had z plus z star, it would be a plus bi plus a minus bi, right? And then we look at the like terms, so we'd have 2a, let me just add it in so it's clear, a, and then we want the bi's, right? So then so a plus a is 2a, so we have 2 a's, and we have the positive bi minus bi, which cancels each other out, so we're just left with 2a. And the next one, z minus z star, which would be a plus bi minus a minus bi. Write that so we don't forget. And then we can rewrite this as a plus bi minus a plus bi. And again, looking at the like terms, a minus a is 0, so we don't write anything there. And bi plus bi gives us 2 bi, right? And then we can do multiplication. So that gives a plus bi times a plus a minus bi. And again, we're going to use the for method, so a times a. The only reason why I continue using these colors because I can't bother to keep switching between to draw the lines. But anyways, nothing more significant than that. A squared and a times minus bi gives us minus abi, and the inner ones, so that's positive abi, and the last one bi times by minus bi. Let me make this a bit lower. So yeah, a squared plus abi should be minus. I'm going to change that. abi plus abi. A squared minus abi plus abi, and bi, positive bi times by negative bi gives us minus b. Let's put it in bracket this time. Bi squared. So again, collecting like terms, a squared, these cancel each other out, so that'll be 0, and we can write this as minus b squared I squared. So this negative isn't rewritten because it's not squaring this negative, so that's why it's still negative if you're wondering why. So I can write as that, and we know that I squared, as you learned before, is minus 1. So that's the same as a squared plus b squared, because minus 1 times minus is positive, so we get a squared plus b squared. And with division, we have z over z conjugate, or z star. So we get a plus bi over a minus bi. Now, let's say we are asked to write in format of in a plus bi format. So in the sense of, maybe not use a plus bi because I'm already using it. So let's say a generic C plus di format. So let's say we're asked to put in this kind of format. So what you'd want to do is multiply by the conjugate of the denominator, which is highlighted. Yeah. So where's the conjugate of the denominator? I don't like the highlight. Conjugate of the denominator. So this conjugate, which is the original one, which is the original equation. So we have a plus bi over a plus a minus bi plus times by a plus bi over a plus bi. So when we times those together, we will get a plus bi, a plus bi times by a plus bi over a minus bi times by a plus bi. Now, because we've already done this maths, we are just going to use what we already have. So a plus bi times a plus bi looks like this one here. So it looks like this one right here. So it's going to be the solution a squared plus 2ab I minus b squared. And this will be over a minus bi times a plus bi, which we've done earlier here. So that's a squared plus b squared. And yeah, so here we'd have a real format, and then obviously, because this is a real number, you can just, for example, just a squared plus b squared, a squared plus 2abi minus b squared. So if I was to write in that format, so do you know what, because in that format it would usually be numbers, so it'd be easier to write. So if I was to write more like this, that would be something such as a squared plus minus b squared, because these are the real terms, over a squared plus b squared, and then the imaginary terms would be plus 2ab I a squared plus b squared. So that would be in the C plus di format. So that was some examples with complex numbers. There are, again, these, what I've used is generic forms. So you'd mainly get questions. Let's have a clear page. So you'd get questions such as, you know, you could have 2 plus 3i times by 4 plus 5i, which I will not go through in this video. I'll explain in a later video, and then I'll go further into other aspects of complex numbers. But it can be something generic as this, but the general formula, how you'd calculate with the general formula, is essentially how you'd calculate with these kind of questions. So the same process essentially, so you have to really focus on the process, not necessarily focus on I need to remember this identity or that identity as much, though it can be helpful when you know you come up against conjugates, for example, but or again you're multiplying, adding the same numbers. But if you get something like this, focus on the process. So really learn the process of calculations. So I thank you for listening and hope to see you next time.